Yeah. So, dear students, welcome back to our NPTEL online certification course on analog electronic circuits. Myself Pradeep Mandal from E&EC department of IIT Kharagpur. Today's topic of discussion, it is frequency response of CES amplifiers, common emitter and common source amplifiers, considering high frequency model of BJT and MOSFET. In fact, we already have started about this frequency response of CE amplifier and CS amplifiers, but there we did not consider capacitances associated with the MOS transistor itself. So, today's discussion, it is we will see what will be the impact of the capacitances associated with the devices, the transistors, on its frequency response, particularly for common emitter and common source amplifier. Compared to our overall flow and overall plan where we stand today, it is we are in module 4. We have done quite an extent about the frequency response of common emitter and common source amplifier. Today we will be extending that for frequency response considering high frequency model of BJT and MOSFET transistor. So, the concepts we are planning to cover today is the following. First of all, we like to highlight the points that the impact of the high frequency response on the frequency response of CE and CS amplifiers. And then we will see that there is a need of some theory proposed by Miller called Miller's theorem, and then we shall use that Miller's theorem to calculate effective capacitance associated with the transistor in the frequency response. And then we shall see the need of frequency response analysis for a special kind of circuit, namely RC followed by R and C in parallel. So, this frequency response of this kind of circuit we have not discussed. We have discussed only RC and CR circuit, but here whenever we will be talking about the equivalent circuit of common emitter and common source amplifier containing the capacitances coming from the transistor, then we will see that there is a need of RC circuit followed by CR circuit. So, that is what we have to consider. So, we will be having RC and then R and C in parallel. So, this kind of circuit we have to consider, and then after that we will be talking about some numerical examples. So, this is what the overall plan. So, let me look back what is the frequency response we have discussed for common source and common emitter amplifier. So, this is recapitulation, as I said, recapitulation of whatever we have discussed so far. So, here we do have the CE amplifier, and here is the corresponding small signal equivalent circuit for that. And so, likewise here we do have the common source amplifier and its corresponding small signal equivalent circuit is given here. So, note that in this model, in this small signal equivalent circuit, for this transistor we do have R pi from base to emitter terminal, and then we do have GM into VBE. In fact, this will be VBE. So, this current source, it is basically voltage dependent current source. In addition to that, we may consider RO, but whatever the model we have considered so far, it does not include the inherent capacitances associated with this transistor, namely base to emitter terminal capacitance called C pi, and then base to collector terminal capacitance called C mu. So, if you consider these two capacitances in this equivalent circuit, we are expecting we will be having a C mu part here and then C pi part here. So, likewise, if you see the common source amplifier, here in the model of the MOS transistor, we do have the voltage dependent current source G m into V G S, and then we may consider from here R D S, but so far we have not considered inherent capacitances of the MOS transistor, namely gate to source capacitance C G S and then C G D. So, if I consider that C G S and C G D, what we are expecting that we will be having C G D here and then C G S here. Now, if I consider generalized model, and here we do have the generalized model of the two amplifiers, namely common emitter amplifier and common source amplifier. So, what we can say that the dotted portion is the macro model of the voltage source, or rather voltage amplifier, where we do have this is the input port and then this is the output port. Within that we do have output resistance, input resistance, and then also the voltage gain. Now, if I consider this C pi C mu, what we are expecting that from say input to output node, there will be one capacitance. So, likewise from input to ground, there will be another capacitance. Now, this capacitance, input port capacitance for CE amplifier, it represents primarily the C pi part, and then if it is a common source amplifier, then this capacitor represents C G S part. On the other hand, the input to output port bridging capacitance, this one it is representing C mu for common emitter amplifier and then C G D for common source amplifier. Okay. So, in summary, so far we have discussed these two small signal equivalent circuit, and there we have seen the frequency response. Now, in our present discussion, we need to consider two more capacitances in our discussion, and that will lead to a frequency response, particularly for high frequency behavior. So, what we have to consider now, it is given here, as I said just now, we need to consider C pi and C mu for common emitter amplifier. Likewise, here we need to consider C G S and C G D for common source amplifier. So, this C pi or C G D, depending on whether we are talking about common emitter or common source amplifier, that increases the input capacitance, or that contributes to input port capacitance. And then we do have C mu or C G D, it is the bridging capacitance between input and output terminal. Now, we also consider, since this C pi and C mu, effectively they are providing input capacitance, input parallel capacitance called say C in. To see its effect, it is also we consider the source resistance R S. Of course, if I do not consider source resistance, even if you consider say input capacitance, in the frequency response it will not be having any effect, because the signal applied at the primary input, it will be directly coming to the input port of the amplifier. On the other hand, if I am having this R S, if I consider the source resistance R S and then in presence of C in, I will be expecting one RC circuit, and naturally that will affect, that will change the frequency response of the amplifier. So, while we will be talking about the frequency response considering high frequency model, we do consider this non-zero value of this RS here and RS here. So, we consider the source is having RS here and this source is also having source resistance RS. Okay. So, if I consider this model and this model together, we do have generalized model which is given here. So, we do have C3 representing either C pi or CGS. Likewise, C4 it is representing C mu or CGD depending on CE or CS amplifier. So, I should say this is the generalized model of the amplifier, whether it is common emitter or common source, that can be analyzed by considering this circuit. So, here while we will be talking about the frequency response, what we can see that impact of these two capacitances we have to consider. And in this frequency response, of course, okay, I have committed a small mistake. In this circuit, we should be having C2 here. So, this is the C2 and this additional capacitance, whatever the capacitance you are putting here, that is basically the CL. Instead of C2, it is CL. Okay. So, now our task is to find the frequency response of this equivalent amplifier representing both common emitter and common source amplifier. So, to analyze this circuit, let us try to see that what are the additional thing we have to do. Yeah. So, if you see carefully in this circuit, as I said, okay, again I have repeated this mistake. We should be having C2 here and then this should be CL. Now, as I said that this C3 it is the input port capacitance, and this input port capacitance it is forming RC circuit with this RS and whatever the equivalent parallel capacitance we do have. So, it is introducing additional RC effect at the input port. Earlier, in absence of say RS and R3, we used to consider only C1 and R1 to get the frequency response. Now, we do have this resistive element and this capacitive element. In fact, we also have this capacitive element, but before we translate this capacitive element, we need to be careful that C4 it is connected between the input port of the amplifier and the output port of the amplifier. So, we need a special treatment to translate this C4 in terms of or into two equivalent element. One is at the input port and another one it is at the output port. Either we can consider here or here. Now, I must say that this splitting of this C4 capacitance, one for input port, another is for output port. It is normally done by a theory proposed by Miller, which is commonly known as Miller's theorem. So, before we go into the detailed analysis, let me go through this Miller's theorem first, and then we split this C4 into these two equivalent component, and then we will be going for the frequency response of the amplifier, right. So, and the other point I like to mention is that whenever we will be talking about the frequency response considering say R pi C pi and C mu or CGS and CGD, we may consider that whenever these capacitors are prominent, the C1 and then C2 they may be successfully allowing the signal to go through this. So, for simplicity, whenever we will be talking about the effect of C3 and C4, we may short this one. So, that you have to keep in mind, mainly because the typical value of say C1 and C2, if you see these capacitors may be even higher than microfarad. On the other hand, typical value of say C3 and C4, they may be in the range of 10 picofarad. Okay. So, naturally the frequency range over which we will be considering the effect of C3 and C4, there you may consider that C1 and C2 effectively they are simply shorting their two terminals. Okay. Yeah. So, now we like to go into this Miller's theorem and try to see what is it and how we split the input to output bridging capacitance into two parts. One is for input port, another is for the output port. Now, in general, here suppose we do have one amplifier and let me consider the signal at the input, it is voltage. So, likewise we do have output signal also in the form of voltage, and then we do have the main amplifier A, which means that VO equals to A times V in, right. So, the signal it is going from left to right. So, we do have input port and then we do have the output. So, you may say whenever you are talking about VO, we are considering the voltage at this terminal with respect to common terminal called ground. Likewise, at the input we are feeding the signal V in with respect to the common terminal. Now, we do have this bridging element. So, in general it may be resistive, it may be inductive, or it may be capacitive, or it may be combination of that. But whatever it is, this element it is bridging the input port and output port. Now, this input port to output port relationship, signal relationship can be represented by this one, excluding this Z element, the bridging element. Now, in presence of this Z, that makes the analysis little complicated. So, a better approach and efficient approach is to split this capacitor or sorry I should say this Z element into two equivalent element. One is for the input port, which is connected with respect to common node ground, and let you call this is Z1, and since the other terminal it is connected to the output port, we also need to consider its effect before we remove it, and let me call this is Z2. So, we can say that effect of Z it is getting captured by this Z1 and Z2. So, we can say once it is getting translated into the its equivalent parts, then you can remove this one. So, that is what this diagram it is representing, that we are splitting the bridging element into two equivalent part called Z1 and Z2, one for input port, another is for the output port. Now, when do I say that they are equivalent? So, first of all, if we feed a signal V in, then if I call that these two circuits are equivalent, and then if we feed the same signal V in, then the condition for this circuit and this circuit should be same, which means that if I am feeding a voltage here and then whatever the current supposed to be flowing through this element, that should be same for this circuit also. Now, for this circuit, the current at the, if I call say this is I1. So, for this case the current expression I1, it is equal to V in minus V o divided by the impedance Z. Now, we also know that V o equals to A times V in. So, this can be written as V in multiplied by 1 minus A. So, by replacing this V o by its expression, we are getting V in divided by Z. Now, on the other hand, if you see in this case, and if I call this current, it is say I1 dash. So, I1 dash, we can write this is equal to V in divided by Z1. Now, to claim that these two circuits are equivalent, we have to equate these two currents, or these two currents should be equal. And so, we can say if I equate these two, what we are getting here, it is Z1 equals to Z divided by 1 minus A, right. So, likewise, if I say that these two circuits are equivalent for the output port, then similar kind of things we can do for the output port. So, please try to remember this relationship Z1 is equal to Z divided by 1 minus A. So, then if I consider output port, and if I stimulate this circuit by say V x, or instead of calling say V x, say this V o. So, if I say that this V o, if it is coming here, so let us not stimulate, let us not stimulate. Suppose we are applying V in, and then we do have V o here, and if the voltage here it is V o, the current drawn through this circuit, it is say if I call I2 dash. So, I2 dash, it is equal to V o divided by Z2. On the other hand, the current flowing through this circuit, if I call it is I2, and in this case I2 equals to V o minus V in divided by Z, and we know that V o equals to A times V in. In other words, we can write V in equals to V o divided by A. So, this V in you can replace by this expression. So, what we are getting here, it is V o multiplied by 1 minus 1 by A divided by Z. Again, if I say that these two circuits are equivalent for this output port, then we can say that this current and this current expression, they should be equal. So, if I equate this with V o divided by Z2, so that gives us the expression of Z2 equals to Z divided by 1 minus 1 by A, or we can say that this is equal to A divided by 1 minus A into Z. So, in summary, these two circuits will be claimed as equivalent, provided this Z1 equals to Z multiplied by 1 minus A, and then Z2 equals to Z into 1 minus 1 by A, right. So, yeah, and so this is what the whatever it is called Miller's theorem, and as I said that this Z, it may be capacitive, it may be inductive, or it may be resistive element, or it may be combination. Now, in our application, in our today's discussion, we do have one amplifier, and then we do have input to output bridging capacitance, either it may be C mu or it may be CGD depending on CE or CS amplifier, and then we can try to see what will be this capacitance. It can be splitted into two parts, one for the input port, another is for the output port. Okay. So, in the next slide we consider a special case of this Z, and we consider this is C, and then we will try to find what will be the corresponding equivalent capacitance we do have here and here. So, yeah, so here we do have the circuit of our discussion, namely we do have this amplifier and its gain it is A, and we do have this C, it may be, as I said, it may be C mu or CGD, let you call it as C, and this capacitor it can be replaced by its equivalent two parts, one is for input port, another is for the output port. And how do we say that this is equivalent? So, the impedance of this capacitance, which is 1 by S into C in, should be equal to 1 by S into C multiplied by 1 minus A. Sorry, this is divided by A. This is divided by, yeah. Now, if I rearrange this equation, what we are getting here, it is C in equals to C multiplied by 1 minus A. Note that here this, whenever we are defining this A, we consider VO is equal to A times V in. Now, in case if A is having minus sign, so that means this part it will be getting plus. So, that you have to keep in mind whenever we will be talking about the actual circuit. On the other hand, the 1 by S C out, so that is the, you see, Z 2. So, this was Z 1, this is Z 2. So, this is equal to 1 by S into C into A divided by, or I should say this is multiplied by 1 minus 1 by A, right. Okay. So, that gives us C out equals to C multiplied by A minus 1 divided by A. In fact, okay, so these two equation it will be used for our analysis, and this is valid even if you consider the finite output resistance. So, in this case of course, the bridging element, it is not connected here, instead it is connected after the resistance, because this may be part of the model of the amplifier. So, we can say this is the Thevenin equivalent resistance of the amplifier output port, right. So, even for this circuit, if I consider the signal coming here and the signal coming here, they are almost equal. So, if I say that even though we do have this resistance, if I say that this VO, it is practically V in multiplied by A. So, then also we can use this relationship, namely C in equals to C multiplied by 1 minus A, and C out equals to C into A minus 1 divided by A. Now, in case if you want to really consider this R O, then this A part, so this A part should be replaced by whatever the gain you get from this point to this point. So, in case the corresponding gain from here to here, it is A dashed, then this A should be replaced by A dashed, this A should also be replaced by this A dashed, right. So, depending on the situation, we may consider this A dashed, or we may say that A dashed it is approximately equal to A. So, this is the Miller's theorem, it will be used in our frequency response analysis. Okay. So, let me take a short break and then we will come back for continuing this topic.